This session is about 45 minutes, but this is the goal was here to hear different voices from people who are have been thinking about or working in cloud infrastructure space. So first up, we have Albert Greenberg and Ujwala from Uber.
Hey, thanks for Tool. So first, it's fantastic that you've started this Cloud Research Center. What took you so long? It's awesome. We're really thankful to be able to speak in it. And I saw some familiar faces in the room. Wish I could have been there, but I do hope to visit. This will be not so much what goes down in the metal of a cloud, but kind of what rides on top. And I'll cover a couple of things about people and then about trends in software-defined data centers where you're building on top of the metal. Okay. And Ujwala is going to do the heavy lifting. So first, as a community, we don't talk enough about diversity, and we're not diverse as a community. So when I get a chance to speak to technical groups like this, I talk about diversity. So at Uber, for example, we have a large set of ERGs investing in different diverse groups and growing diverse populations. And there's really not an advertisement for Uber here. It's just that all of us need to invest to improve diversity generally, and that it takes effort and commitment. So there are a couple of programs here for career development, how to get through the ups and downs of interviews and get started in your career, as well as special internships, sponsorships, mentorships, all aimed at growing diverse talent. So it's a big deal, and so I talk about it pretty much every time I get a chance to meet with a technical group. Okay, next slide. Let me get to the what I mean by a software-defined data center. So, at Uber, we developed, let's call it the IaaS layer that allows you to abstract the network and the hardware, the SSDs and the GPUs, this and that. So you can just treat the infrastructure as a pool of resources, growing and shrinking that pool as needed. That is essence, gives you the flexibility to do a lot of software development on top without a lot of friction. So we built this kind of IaaS layer that does this abstraction for us. And then, what are you going to do with it once you've got it? And, we do a lot of stuff with it. Uber is kind of like a giant machine learning match in the cloud and a fulfillment. People and things move where they're supposed to go, and folks get paid. And all that happens on top of this infrastructure. And a key component is the real-time and batch analytics that's running. We call them machine learning ops. So there's a ridiculous number of machine learning ops per second. I don't, Ujwala might know, but it's maybe 1 million or so. It's just crazy. There's so much going on to make these decisions on moving people and things around the world, and all on top of this abstracted software-defined data center. Now, a interesting element to this is use of open source. Open source doesn't solve any problem. Open source, though, is a building block that can be used to solve problems. And it's a big responsibility to take on. Uber does a lot of writing and also consuming of open source. And so the talk today that Ujwala is going to give is going to focus on this real-time analytics stuff and batch analytics stuff built on open source called Presto and Pinot. And it's kind of like the API and the engine for this kind of work. There are other APIs and engines out there, but this is the one that Uber uses and contributes to. So you wonder why. Why did we pick this one? And what is the checklist, if you will, toward picking any kind of open source. And by the way, this will change over time. There's a life cycle to this stuff. And I saw Dave was talking here, so maybe he mentioned Sonic. You know, it's open source goes through, you know, there was a time when that was small and now it's not so small. And so this is more or less not at the very early days of an open source, but in a not too, you know, at the toddler phase of open source, what you look for. And there are three things. So we call tech readiness, adoption risk, and community attributes. So, you know, again, you know, open source is a big investment. So you want to make sure that either the tech is ready or it's got enough engagement that you feel it's going to get ready. And one thing you look for is industrial adoption. You know, Martin's on the call. I remember him at one of our dinners talking about how many GitHub check-ins or pull requests, you know, is going on. You can just look and see if there's good engagement and from what communities. And, you know, conferences and this and that scale, you know, Jan Stoica is going to be talking and look at all the Apache stuff that he's driven with Spark and other things. So you can kind of see if there's a snowball going that you want to buy into. And then, you know, the adoption risk. This is a very strong variable. You can start off, you know, roaring and then start not be roaring a year later. And so you need to make sure that you have the talent in-house to integrate these things and maintain them and sustain them. And by the way, that'll change in time, right? So Mesos was the rage, now Kubernetes is the rage, you have to move. And, you know, then community attributes, there needs to be a reasonable governance model so you don't feel like you're going to get locked in. And there has to be some sign of active development. These are all things that, you know, when you make a decision, you consciously sort of create a contract that if you're going to go this way, there's going to be a big investment, pros and cons, and you're going to pick things that satisfy these three checklists. And we do this in a big way at Uber. With that, let me turn it over to Ujwala.
Thanks, Albert. Hello, everyone. Good morning. My name is Ujwala, and I lead the real-time analytics team at Uber. So before we jump into my talk, I want to reiterate over what Albert said about the Uber's commitment to DEI. To share a personal story, I joined Uber 4 years back, and many people suggested to me that, oh, I should rethink my decision to join the Uber. But in last 4 years, I have got so many opportunities to grow personally as well as professionally. And I work with very diverse people and they bring their diverse perspective to the table. So that's kind of makes a core of Uber, and I really believe in the Uber's commitment to that. So coming back to our topic today, I'm going to talk about like how what is the real-time analytics platform, how we use the various features provided by the underlying distributed systems, and how we leverage the Uber's private cloud to facilitate like so many operations at scale to achieve the reliability. So when we talk to the various customers at Uber, their requirements can be put into the three different buckets. The first one is the real-time and actionable insights. As you can see on the left-hand side, the restaurant performance view. So this is the portal which is built by the Uber Eats team for all the merchants across the globe. And there are like close to millions of restaurants on the Uber platform. And they are looking for how their restaurants are doing on the platform. And they want to know about like how much sales are they making in the last few days to few years. The second category is the time sensitive decisions. And this is, we have the demand and supply management example in the middle. Every minute there are like hundreds of orders being created and they are fulfilled at the same rate. If there is not a balance between the demand and supply, it can create a marketplace mismatch. So if there are a lot of orders but not being picked up, so that's not a good experience for the users. And also if there are very few orders and like a lot of couriers to pick it up, it doesn't give the flexibility for or enough benefits for the couriers on the platform. So the time sensitive decisions makes it critical to maintain the healthy marketplace. The third category is the user engagement growth. Uber has multiple apps like Uber Eats app, Uber Rides app, or Uber Freight app. And what we are looking for is how to increase the Uber engagement with this user engagement with these apps, and so that we can provide the meaningful information for users to make sense of. So at the nutshell, what we are looking for is the fast access to the fresh data at the scale. So the fast refers to the very low response time. Fresh refers to the very high data freshness, because Uber's business is very highly real time in nature. And then as the scale refers to the throughput, whether it refers to the ingestion throughput or whether it refers to the query throughput. Um, and considering all these requirements, we have come up with our real-time analytics platform, which is based on two open source technologies, as Albert mentioned. One is Apache Pinot and the Presto. Uber is one of the biggest contributor to the contributor as well as the consumer of the open source technologies. And even though like we support not just a single org within the Uber, we support almost tens of orgs. To name a few: the Uber Eats, Uber Freight, the ads, fulfillment, Michelangelo, which is our machine learning platform. For today's discussion, I want to focus on the Uber Eats area because that is something everybody here can relate to it. If you are using the Uber Eats app, you are already using this feature in some or the other capacity. So if you are looking at the search history, the search items that you did in the last few days, to the popular near you, like what are the popular or the trending items near your city, or what are the different restaurant people are ordering from in your locality. So all this real-time data is being powered by our platform that we have built. And the second is the Uber Eats Manager, as I mentioned earlier. This portal is being used by almost a million users, a million restaurant owners, to track very key metrics for their business. They want to know about the sales insights or the conversion funnel. So conversion funnel refers to how many people are looking at your restaurant, how many are actually putting the items into the cart, and how many are checking out. So like looking at this data, like they want to know where they can do the better planning. Apart from that, there are like other key metrics about the top selling menus, or like how much they are getting by spending the money on the ads platform, or putting up the ads for the restaurant. And all this data is when we are saying that like okay, it is powered by our platform, it creates some challenges at the Uber scale. The first one is the substantiable variability in the use cases. Like it's not just one Uber Eats. There are like other platforms that we serve. There are like large number of tables with the various data sizes. There are like tables which are very small because they are looking only for the last few hours of data, versus there are like some use cases which are looking for the last few years of data. So that can add some variability. The bursty traffic patterns or for the ingestion and query. Because Uber is a business which is like really busy over the weekends and holidays compared to the normal weekdays, we see a tremendous spike in the user queries over the weekend compared to the weekdays. And then you have to do a resource planning that aligns with that pattern. Noisy neighbors. So if you are combining and tackling all these multiple use cases into a one shared cluster, you obviously run into a noisy neighbor problem where one queries on the one use case are causing the issues for another. So there are changes in the query patterns, table configurations, and the type of queries they run. To solve these problems, and again, like we haven't solved all of the challenges and there is a lot of problems unsolved, but as of now, I'm going to talk about how we are leveraging the cloud infrastructure of the Uber to solve these problems. The first one is like the resource allocation, right? So on the bare metal, we have the one host and one server, one process is running on that. And that itself is not really sufficient. Either there are like resource plan challenges, or like you are not using them effectively. So after migrating to a private cloud, we are like combining the multiple processes into the one host, and that is basic the virtualization principle, right? Like so, we are utilizing the resources to the best of the capacity. The second is the reliability, and then that matters because even if your platform is down for a few seconds, it can cause a very uh, high business impact for the Uber. And the way we achieve is that like the first thing is the isolation with the multi-tenancy. The Pinot or the Presto, these are the services they have. Their architecture supports the multi-tenancy, and we also use the cloud to make sure that we are creating a separate clusters or different tenants within the cluster for the different use cases, so that we are not bottlenecked by one or like not there are like not a single failure point in the system that is caused. The cloud automation, they provide us the easy way to build this and expand this tenant. So for example, there are like larger tables, so you can expand the servers to add more servers on demand. If there is high QPS, so that means there are like brokers which process these queries and then send it to the servers, like they are getting bottlenecked. So you have easy way to expand the broker tenant. The second one is the scalability, and auto scaling the resources. As I said, like the horizontal scalability is the key, and especially like this, the Pinot, Apache Pinot also supports the Lambda architecture. So that means we are ingesting from both streaming resources like Kafka and also the batch resources like the HDFS at the same time, and then providing the unified view to the users. And horizontal scaling makes it possible to expand your resources on demand and with just few clicks on the our cloud UI, like, and it's very easy to use, like, and we do not have to spend a lot of efforts into managing these clusters. Right sizing the tenants based on the usage. As I said, like there are different traffic patterns and the different usage patterns, and there should be a easy way to add and also remove the remove the nodes from the cluster, because if there is not much usage on the one cluster, then you should use those resources for the another. And this has to be the transparent to the use cases or the services that are built on top of the cloud. The third is the policy-based capacity and scaling recommendation. We have the many compute services. We already does the auto scaling based on the CPU memory disk utilization. We also look at the organic growth of the service, and also if there are any upcoming product launches, like we have to adjust our resources accordingly. So there should be an easy way to provision this. And based on the performance regression trends in the last few days or like last few weeks, we should be able to adjust the resources. The next one is about the quality, because we are serving the millions of users who are using our platform every single day. And like even though our platform is like self-serve, like where user can come and create their data sets, that can add a lot of operational overhead. And our main goal is that even if there is operational overhead, we should have a ways to tackle that with the automation and not not let the human errors impact the business. So we use the cloud for single click cluster creations with hundreds of hosts, especially like there are like some use cases where we are using thousands of nodes in a one cluster, and within that cluster we are creating the tenants. So the easy management is really key to the business. The automated node replacement. So if there are some things happening, or like or there are like some bad nodes in the system, it's a detection is the first thing, and then like how we can provide ways to like repair those in place, or also like provide a ways to automatically do those node replacement in a wide cloud environment. Again, as I said, like we have not solved all the challenges, and there are like a lot of areas of improvements for us. The first one is that it's easy to do the resource planning for the compute services, but it's equally hard for the stateful services because the data is in the picture, and then you are working with a lot of data migration and the copies. Automatic data optimization based on the traffic pattern. If there are like some specific expensive query shapes that you need to handle on the ongoing basis, so you should have the automated way to identify how I can optimize this query so that it doesn't become a bottleneck in the long run. Self-healing, then auto recovery. So finding finding the problem, and then how we coming up with the ways that can heal that problem in place is the really needed. And then actually we are continuously improving the technologies, like whether it's a Apache Pinot or Presto, but we are also adding a lot of features to our internal cloud to make this easily possible. And the tier storage, which is the traditional problem in the industry, and then it's also true even for the today's world. So we want to know actually which data needs to be tightly coupled with your technology and which needs to reside locally, versus the data that can just go to the different tiers of the storage, or like in the cloud, or even the more of a cheaper options in the storage. So that is another area that we are evolving. So yeah, that's about our talk. Thanks for listening. If you have any questions or concerns, please reach out to us. And we also have the Good Engineering blog forum. Like if you want to check out the information about the new trends, feel free to check out the engineering blogs. Thank you.
Next, we have Jan.
Good morning, everybody. Very happy to be, though I hope that I'll be in person, but I'm now in Romania, actually. In the next 15 minutes, I'm going to talk about sky computing. This is a new lab we started at Berkeley earlier this year. So what is sky? Well, one way you can think about sky is that internet for the clouds. So basically, sky aims to abstract away clouds as the internet abstracts away different networks. So let me give you a simple example. Consider a canonical machine learning pipeline consisting of three stages: data processing, training, and serving. And now assume that the input data has some personal identifiable information that we want to remove before we are training. And also we want to minimize the cost of running this entire pipeline. So what Sky can do using the top three public clouds is to run the data processing stage in Azure to leverage Azure confidential computing for secure data processing to remove the PII from the input data. Then after the PII is removed, feed this data to send this data to GCP to leverage TPUs to train a model, and then the model ship it to AWS to use the new inferential chips. Now, it is worse. Well, and does it work? So here it is, it's an example of using BERT. It's a popular neural network. We are fine-tuning it. And we train it on, we fine-tune on a review data set. We assume that one of the column is contain PII. And after we train the model, we serve 10,000 queries. So now, if like today, you run the entire pipeline on a cloud. So if you were to pick a cloud, because the first stage needs to run on hardware enclaves, and then we have to run it today in Azure, because Azure, like I mentioned, provides Azure confidential computing platform. So if you do that, the pipeline takes around 11 hours, and it costs a little bit over $100. But now with Sky, like I mentioned, you can run only the first stage on Azure, and then the training you can run on GCP and inference model serving on AWS. And by doing so, you can reduce the running time by 47% and the cost by 61%. Obviously, when you have this in this pay-as-you-go business model, you have a nice correlation between the running time and the cost. The faster you run, the less you are going to use the resources, the cheaper it can be. By the way, in this case, we also take into account the egress cost. Now, so basically what Sky tries to do is to take us from this world in which you need to customize your application for every cloud, and to move toward in which the application transparently is running across different clouds. There are three components, basic components of Sky. The first is compatibility set, which is a set of public services which are possibly implemented and deployed offered by multiple clouds. Then it's a intercloud broker, which is the main component of Sky. And this is an application which runs on intercloud broker, has transparent access to these services across multiple clouds. And then we do think that we believe that in the future, different clouds, especially clouds which have complementary strengths. So one cloud is extremely strong on the storage, the other one in hardware accelerators. They can have free peering arrangement, very much like today, different players in the internet. So now, here are some unique properties of Sky. So while I mentioned Sky abstracts away the clouds, it does not require a uniform API to be implemented by all clouds. It just leverages opportunistically the services which are even provided by a single cloud. It also leverages services at all layers of the software stack, not only like VMs or things like Kubernetes, but also higher level services like Spark and Kafka, which are provided as hosted service by many clouds. And also we'll leverage, obviously, similar though not identical services like the object stores, using, in this case, simple shim layers. So all of these services are part of the compatibility set. Just to be more specific here, the compatibility set consists of open source based services provided by clouds, like hosted Kubernetes, AKS, GKS, and EKS. Hosted, say, Spark, like HD Insight and Synapse provide hosted Spark services from Azure, Dataproc from GCP, and EMR from AWS. Then there are open source based services provided by third parties like Apache Spark, hosted Apache Spark from Databricks, Apache hosted Apache Kafka from Confluent. And then there are the now proprietary services provided by clouds like GCP or SageMaker. And like I mentioned, similar services like object stores, like S3 and Azure Blob Store. And finally, there are proprietary services provided by third parties which can run on multiple clouds like Snowflake. So now, the next component is the intercloud broker. And this intercloud broker, the way you can think about it, it enables a two-sided market between the applications, and their requirements and the user requirements, and the services which are provided by different clouds. And there can be more than one intercloud brokers, and the intercloud brokers can be specialized. They can also charge a fee for the service. So it's pretty open playing space here. Now, under an intercloud broker, you roughly have a few components. A service catalog, which actually aggregates the information about the services across clouds. This means APIs and their versions. It can be, the particular mechanisms and particular ways to instantiate a service, tear down a service, cost information, and things like that. And then the users provide an application specification. You can think about this like a DAG, like something like Airflow, job, for instance, something like that. And which consists about this kind of big task. These are big tasks in the sense these tasks are not like an RPC. It just it's like something like a stage in a pipeline. It's like training or serving or things like that. And based on this information and the user preferences, like minimize the cost and latency, the intercloud brokers take this information, matching the services which are available from the service catalog, and compute a physical plan, and then run different parts of the jobs on different clouds. Then when it comes to billing and accounting, there are two ways. One, the user can have individual accounts with different clouds. And another way, the intercloud broker has accounts for different clouds. And then the user has one account with the intercloud broker. Now, when we started this project early last year, one pushback was, good pushback, how this will happen. Like the many players may not want this to happen. But actually, we do believe this will happen. We do believe this is inevitable. And for three reasons. One is compatibility set is growing quickly, actually. There are a number of OSS-based hosted services. It's actually increasing quite fast. And the second thing is that competition is driving cloud proprietary services to be more alike, actually, like blob stores, instance management, and things like that. The second is that obviously users want it, and there is a variety of reasons why users want it. One is to satisfy the data and operation sovereignty. There are more and more regulations which requires that the data to not be only stored but processed by data center in a particular country, and data center which may be managed by the nationals of that country. Then is a user desire to leverage best of breed services and hardware. You want to leverage Azure, confidential computing, TPUs, and many other accelerators, which are provided by one cloud. Then it's aggregate resources across clouds. It's, we say that the cloud is elastic, but if you look at the scarce resources like GPU, actually it's not. We know actually some of the users, which today in an ad hoc manner Actually, they use multiple clouds for training because they don't have in their account enough GPUs in one cloud. Obviously, it's reduced cost and latency. It's another reason. And finally, another obvious one is to avoid lock-in. And finally, Sky can start with no help from the existing clouds. You can start with an open source intercloud broker using the existing today services. And we can start with easy cases. We don't need to provide, and we don't have the intention to have something which works for all applications. Okay? Actually, we are building such open source broker. We call it Sky Pilot. And we are targeting right now machine learning training and hyperparameter tuning. And the users are researchers and students, which actually have credits from multiple clouds. So this is what their problem. They have credits on multiple clouds and they want to use them in an effective way to write their papers. So Sky Pilot aims to provide easy of use and cost saving, leverage array for distributed machine learning workloads. And it saves the cost. This is one important aspect. By picking the cheapest cloud VM when you request resources, when you start the job. It's also taking into account the data transfer cost. And here is one example. It's also leveraging aggressively the spot instances. It implements auto recovery at the application level for training and high parameter tuning. And I'm not going to explain because lack of time, this entire plot. This is just training. It's a loss versus time. When using on demand and using spot instances on the same region and spot instances actually across region and across clouds. But the main point here I want to make here is the real example. You can get using Sky running 40% faster than a single region or user spot instances and 70% cheaper than using on-demand instances. Okay? So you have the cake and eat it too. Now, project status, it's our early stages. We have 6 active organizations, probably between 10 and 20 users. It's open source, and we have some, nice quotes from people which attest the fact that it makes their life easier of running their job, training job across multiple clouds, and also that it results in cost reduction. Now, at this point, I'm sure that some of you will ask, hey, what about data gravity? You hear a lot about data gravity. And it's often cited as one of the biggest barriers for multi-cloud. This is egress cost and transfer performance, or moving the database from one cloud to another. And we have another project, Skyplane, try to alleviating these problems. And basically, with Skyplane, we move bulk data both within and between clouds at high speeds and low cost. So here, in this example, we want to move the data from Azure Middle East to AWS Northeast in US. And that's, not surprisingly, not very fast. And for a variety of reasons, like, networking people know that very well, is congestion, is hot potato routing over the internet, so inefficient routing, packet loss, the physical layer, poor peering between providers, and so forth. And we try to solve that using a variety of techniques, many of them very well-known techniques, but we put them together. One is overlay routing. So we don't send the data directly, we send it through some relay region. So instead of going directly from Middle East to North Virginia, we go from Azure Middle East to AWS in India, and from AWS in India to North Virginia, right? So we are trying the long haul to be in the same cloud. Then we use multiple VMs per region to avoid egress per VM egress limits, parallel TCP connections to improve the throughput, and network tier selection. We use, hot potato actually in some clouds like GCP provides us 40% less expensive than cold potatoes, where the traffic is contained in the same cloud. With hot potatoes, the traffic goes out. The cloud tries to send the traffic as fast as possible outside their network. So here is an example for Azure. Moving data from Azure Canada Central to GCP Asia Northeast. Here we have a relay point is Azure Japan East, and we go from 60 to 6.2 gigabits per second, which is direct, going from directly using Skyplane, we can go up to 43.4 gigabits per second, so 6 times faster. These are comparison with GCP data transfers. GCP is red, Skyplane is blue. Smaller the better, and we get performance improvements in both between clouds and within the same cloud, and this is also true for AWS data sync within the same cloud. Finally, before I end, I want to make one point. So far, I talk about multiple clouds, but maybe not surprising, the Sky also is relevant for a single cloud. These are the main properties and the main reasons, why users want something like Sky. But if you look at this one, they apply to a single cloud. Indeed, the data and operational sovereignty. If the cloud has a data center in a particular center, well, you send the data to be processed in the data center. It's also leveraging the best of breed services and hardware. Actually, most of the clouds don't have the most advanced hardware in all regions. Like for instance, something like GCP has more than TPUs in only 2 or 3 regions in the world. You also want to aggregate resources across regions. Like for instance, if you want more GPUs than you have in your regions, you may want to get from multiple regions, or the same thing about spot instances. You can reduce cost if you don't have enough spot instances in your region or the data is, and use a different region, and all of this transparently. The only thing you cannot do is avoid lock-in. So in summary, Sky abstracts the clouds, and without demanding uniform API. And I think this is a very important property because the previous efforts tried to do that, and I think we think this is extremely hard. And leverages services opportunistically at different layers of the software stack. We start narrowly with batch workloads, machine learning workloads, and we just try to make sure that this is going to work well before moving to other applications. And we are academics, so we're really very excited about, like you heard from the previous presentation, it's a lot of exciting research. It touches many areas: distributed systems, storage, security, networking, scheduling, you name it. With this, I'm just ending up. This is a Sky Computing Lab. I told you like started at the beginning of the year. 8 faculty, around 50 PhD students and postdocs, sponsored by Google, IBM, Intel, Samsung, VMware, and a few startups actually, Astronomer, Lacework, and Nextcloud. We show you the interest in the industry and the interest of the newcomers for this, multi-cloud technologies. Thank you.